Good afternoon, everybody. Hope lunch was good. My name is Jim Deloisio. You are here for the Enlightened Structures, Reducing Material-Based Carbon Emissions presentation. And I'm happy to do it with three of my colleagues. And kind of the understory is there are many enclaves of good, professional, thoughtful, creative people doing stuff about sustainability and reducing carbon emissions that you don't always see. So we're going to hear some of those stories today. This is basically structural engineers coming out from behind the curtain to show you what we're doing in terms of identifying carbon emissions and what we can do to reduce the footprints. But just a couple of housekeeping things before we get into it. If you want AIA, BPI, or GBCI continuing education credits for this workshop, you need to sign the form in the back. Hopefully you've got your numbers. NSE cannot provide credits if you don't sign the sheet as proof of attendance. Okay, that's you may have heard that drill before. And at the end, please fill out a session evaluation form. Wait to the end if you can. That's important feedback. Well, we need our feedback. And also, after the last session of the day, okay, well, wait a minute. After this session, there's going to be coffee at 3:30, right on the mezzanine level. Okay, so look forward to that. Please turn off your cell phones or silence them or diminish their volume or whatever the right thing to do is, depending on your device. And I present the four of us. I'm Jim Deloisio. I'm a structural engineer with Klepper, Hahn Hyatt from Syracuse, New York. My co-presenters include Mark Webster, who is in the front row with Simpson, Gumpertz, and Heger. Russ Miller-Johnson from Engineering Ventures in Brattleboro. Burlington. I get those B Vermonts mixed up. Burlington, Vermont. And Mark, Russ, and I are members of the Structural Engineering Institute Sustainability Committee, where we've done some pretty cool things with about 30 other really intelligent and creative structural engineers. And Kara Peterman from Northeast University. She is studying for her PhD. No, not her PhD. She is a grad student. She's a postdoctorate student at Northeastern University. Yeah, Kara and I know each other very well. And Kara and Mark and I are on a PANCOW-funded research program about thermal steel bridging, which actually all four of us have that in common because that's one of Russ's topics as well. So without further ado, let's begin. What we're going to do is we're going to have each of the four presenters talk for 15 or 20 minutes, and then we're going to have the rest of the time for questions. Hopefully there'll be lots of time and lots of questions. This is the requisite AIA slide. And that's the course description that was in the manual. This is what you signed up for, so we're going to try to deliver. And the learning objections with the active verbs. No, I'm not going to read all the slides. Thank you. Okay, the first is my presentation on carbon and structures. And then we're going to get to the other three. Y'all can hear me in the back okay? Okay, so let's begin. Carbon and structures. This is a slide I find useful to start with. We have an issue with our buildings and our infrastructures that we design and build, and that is they are responsible for carbon emissions. Since 1880, the amount of carbon dioxide has increased in the atmosphere by about 40%, a pretty significant deal. A large amount of that is due to the combustion of fossil fuels, but that's not the only thing that has caused the CO2 increase. For structural, the production of Portland cement is a pretty big factor. Which is somewhere around 6% of the anthropogenic emissions of carbon dioxide by humans. That's redundant. Anthropogenic means by humans, but you know what I mean. So that's where we are. That's why we are tackling what we are tackling. We think that as structural engineers, we have a piece of the solution and a part that we can play in minimizing carbon dioxide and CO2 equivalent gas emissions from the atmosphere. This is from EPA, showing that it's not just carbon dioxide, it's carbon dioxide equivalent emissions. Now, I got freaked out about this once because methane has a significantly greater impact of global warming than carbon dioxide. And nitrous oxide is even more, and fluorinated gases are huge. But this is not a chart of the volume of gases. This is a chart of the effect of the global warming potential of the different gases. So carbon dioxide is 84% of the problem, basically, and the number is over a 100-year period. I'm actually glad that I'm a structural engineer and not a climate scientist, because this stuff is actually pretty complicated. And it's not just carbon dioxide that is increased in the atmosphere in the industrial age. It is also methane, nitrous oxide, and also those other very potent global warming gases, which we see in blowing agents for certain insulations and such. Very high global warming potential emissions that really don't exist in nature. So that spike is even more intense, although it's not shown in this graph. Okay, so what I did in my spare time on weekends for fun is I developed a carbon palette. And I'm not a practitioner of life cycle assessment. I am a user of the information of life cycle assessment. It's a very complicated, interesting, fascinating, but thing that I don't have time to do as a practicing structural engineer. What I like is that finally we're at the point where we can grab some data that other people have very carefully compiled, starting with concrete, so that we can quantify the carbon emissions of concrete in a more specific way than we ever had been able to before. The National Ready Mix Concrete Association has jumped to the forefront in the structural materials in developing environmental product declarations. Now, EPDs have been around, but LEED v4 has introduced the idea of product category rules, and from which you develop an environmental product declaration, which identifies the various environmental aspects of the different materials. That includes carbon dioxide equivalent emissions. And they have done a remarkable job. Believe it or not, what they've done is they've got a document, and all you do is click on that little link on the screen, or just go to nrmca.org, and you'll find the sustainability information. They have gotten environmental product declarations for thousands of ready-mix concrete batches, mixes across the country. They've divided the country into 6 different segments, and they've got different strengths of concrete, so you can actually get the various attributes of the concrete that is produced all across the country, including the global warming potential carbon footprint of that material. Fascinating and amazing. It's all in metric, so it doesn't make any sense when you first see it if you're used to imperial units, but I spent some time with my calculator, and I've been able to kind of aggregate some general conclusions. And fortunately, they're nice, simple, round numbers. And a true practitioner of LCA may balk at the simplicity of the numbers, one significant figure. But for working purposes, for going forward and understanding what our carbon footprint is for buildings, I find it very useful. It's about a pound of carbon dioxide emitted into the atmosphere for every pound of Portland cement in the mix. So a 500-pound cement mix per yard puts out about 500 pounds of carbon dioxide into the atmosphere. It's that simple, and that's relatively accurate. Another way to do it is it's about 1/10 of a pound for every pound of concrete placed. So if you are doing it by mass of concrete, that's a way to calculate. And by those numbers, the EPDs show a variance of around 350 to 800 pounds per cubic yard of concrete. With the more cement-rich mixes, the higher content. So there's some strategies that the practicing engineers can do to reduce carbon emissions from concrete, using fly ash and slag to make sure that the use of the fly ash and slag actually offsets the amount of cement so that it's not just added on to the amount of Portland cement. You can reduce the amount of Portland that way in a pretty significant way. We typically start at about 20%. All of our concrete, pretty much all of our concrete has 20% offset of the amount of cement with supplementary cementitious materials. We're only scratching the surface on some of the ideas that we've developed in more detail, but to not overspecify the strength, to use 4,000 when you don't need 4,000, and to minimize the amount of concrete volume when possible. For example, using frost-protected shallow foundations instead of deep 4 or 5 foot deep foundations can make a big, big difference, and we'll talk about that in a minute. There's a downside to any operation, field operation, including construction, diesel vehicles idling, worker travel, etc. But that's kind of concrete in a nutshell. For masonry, there's some similarities here. The actual masonry industry hasn't really developed EPDs for the different block plants, and they probably won't. They've got product category rules, but they are asking all of the different manufacturers to come up with their own EPDs. I wish them luck. And I'm from upstate, and what I've learned in upstate, and it's probably true of most of the rest of the country, is that if you ask your block producer to provide a low cement block, they will. They can usually reduce the amount of cement that they would have otherwise used by about 25 or 30% by using fly ash and slag and other things and just optimizing the mix design. But you have to ask. That frequently is at no additional cost. So if you want carbon reductions for your block, ask for carbon reductions and you'll probably get it. For masonry grout, one of the most common ways to specify masonry grout is the proportion method. It's easy, it doesn't require any field testing, but take a look at those mix designs for the proportion method grout, and you'll find that it's 6.5 or 7.5 bags of cement. Bags, I'm showing my age. You know, 600 or 700 pounds of cement per yard of grout, which only needs to be 2,500 psi. So specify the strength method, require the prism tests, and you can probably cut the amount of cement down by something like half. You want to cut your carbon footprint in half? Just do it. Is this any additional cost? No. The grout's a little cheaper, the testing is a little bit more, but essentially it's a no-cost benefit to reducing carbon. There are other masonry products out there in the Midwest. There's a thing called fly ash brick, which doesn't require any cement or kiln drying or anything. It's basically the contemporary mud brick using fly ash. There's carbon footprint issues with all of the masonry materials that we use. So let's talk about steel. In a real nutshell, there's a couple of different kinds of manufacturing of structural steel. Electric arc furnace in this country is the most predominant way to produce rolled sections. It's essentially the only way that's effectively being done anymore in this country, but there are basic oxygen furnaces around the world that produce rolled sections that have a higher carbon footprint. So averaging 0.0, 0.85, and 1.2 comes out to be somewhere around a pound. Okay, for general purposes, you emit about a pound of carbon dioxide into the atmosphere for every pound of structural steel fabricated and erected. That includes, the incidental erection footprint. So rule of thumb is a pretty quick thing to do. You got 10 tons of steel on a job. What's your approximate carbon footprint? 10 tons. It's that simple. So you don't need a calculator. A colleague of mine once had a client that valued reducing carbon emissions, and I envy him because I've never had such a client. I just do it for fun. What they decided to do is actually specify a range of sizes for the interior columns, the pinned columns, pipes, tubes, H-sections, rolled sections, whatever they were a range of acceptability depending on what they could find, and they found a stockpile of old abandoned pipes, which they inspected, reconditioned, fabricated, and shipped to the site. And it brought the carbon footprint of that steel from about a pound per pound of steel to 1/10 of a pound per pound. So that's a 90% or so reduction of carbon emissions if you're able to have a client that really values carbon reduction. If ever the price of carbon was given a financial price in the market, there's a lot of cool things we could do. I made some assumptions because some assumptions really wildly affect the outcome of the carbon emissions calculations. For insulation, which is significant, I assumed 100% of the blowing agents included in the tally. Does it ever eventually all get back into the atmosphere? It's not clear. And I also assumed that extruded polystyrene uses HFC 134A, which is at this point the most common blowing agent for extruded polystyrene. And we'll see what that means in a slide or two. For wood, it's a very complicated thing because wood is part of the carbon cycle. I didn't include any value for sequestration if the building happens to be very successful and lasts for hundreds of years. You've sequestered carbon in that wood building, but it's kind of hard to bring that back into your calculations. Nominal amount of waste. Construction is a pretty wasteful thing. Nominal worker travel is what I assumed. This is a slide that I show from the Building Green website. They did a study on global warming potential of insulation types. And as you can see, there's two big numbers for closed cell, non-water-based spray foam, and for expanded, oh, I got the circle wrong. It's actually, the circle should be on the bottom number for extruded polystyrene. Extruded polystyrene has that blowing agent, which has very high level of global warming potential, gas properties. So we generally try to stay away from that because it really racks up our carbon footprint of our building. Okay, this is a cool snapshot. If you got 12 workers on building a house or a big house or something, each driving a truck that gets 12 miles a gallon, driving 12 miles to and from the job site for 12 weeks before they finish the building, do the math and it's about 14,000 pounds of carbon dioxide just from the worker travel. Depending on the location, depending on the fuel efficiency, and depending on the workers' travel habits, that can be a very significant footprint of just worker travel. Dematerialization is a really cool thing, but you do have to be careful. It is the quintessential enlightened structure. You know, you can lighten your carbon footprint by lightening your structure, but you do have to be careful. Although a ton of steel saved is a ton of carbon dioxide equivalent emissions from that footprint eliminated. In the case of steel, it would be a ton. But you must maintain all of the structural integrity, of course. Structural engineering is a very critical pass-fail test proposition, basically. There's also serviceability issues, but we cannot compromise the amount of material that will cause any kind of structural compromise or adaptability or potential for reuse or future usage, which Mark is going to be getting into in his talk. The tricky thing is dematerialization, careful optimization of the material volume requires more engineering effort. So if you've got a project where you've got an owner that's willing to pay a little bit more for engineering services, maybe you'll want to engage in dematerialization. I don't have any such clients. Haven't for a while, actually. And it may or may not be cheaper. If you're looking at construction cost, of course, you can't really do anything in today's market without carbon being valued in the market, without keeping the price the same or having it cheaper. If there's anything that increases the price, all of a sudden, it's no matter what the carbon emission savings are, there's really not much interest in advancing that idea. So here's what I did in Syracuse on a winter weekend for fun. That's what we do in Syracuse on weekends for fun. Now imagine a two-story office building, 80 by 25, 10,000 square feet. The perimeter is 410 linear feet. 12.2 foot floor to floor because that made the numbers really easy. It's 10,000 square feet of perimeter, which is 20% fenestration and doors and 80% opaque walls. Okay, you got a mental image of that two-story building? Basically, you don't have to read through all of this, but it's a very contemporary construction. Open web steel joists on the roof, metal deck, insulation on the roof. We use the concrete floor slab composite deck with reinforcing first floor concrete floor slab with reinforcing to minimize curling, because that's what we do, because we don't get callbacks when we put reinforcing in the slab on grade. Exterior walls, sheathing, vapor barrier, studs, fiberglass bat insulation between the studs, sheathing, and we put brick on the buildings, because a lot of our clients like brick on their buildings. Perimeter foundations, standard, interior spread footings, so that's the picture. It is contemporary construction without any changes to the typical, okay? And this is my little spreadsheet with approximate carbon dioxide emissions for the different materials and for the different volumes. Okay, what that totals, 34.9 pounds per square foot. That two-story building, the structural and finished systems that I modeled here were responsible for about 35 pounds. Yes?
Can you just clarify one thing? Are we talking about the emissions from fundamentally primary energy there?
I'm not talking energy at all. I'm just talking about the carbon emissions of those materials, okay, based on the environmental product declarations and what we know of other materials. It's not energy, it's about carbon. I don't know if that answered your question.
I'll reserve it. Thank you.
We'll talk later. Anyway, being an engineer, I put it on a graph. This is what it looks like. With the green being carbon, concrete, a little more than a quarter of the footprint of that building was attributable to the concrete. Structural steel, another quarter. Cold form metal framing, which is what we use for the walls, another slice. Insulation, a good chunk, because we use some XPS in the foundations. And other, which was mainly windows. So then we try to do a few things to shake things up a little bit to see what the impact is, what the sensitivity is of these changes to the carbon footprint. So frost protected shallow foundations. Then we added supplementary cementitious material for our concrete. And then we used rock wool instead of XPS. And then we used wood structural framing and studs. Both the structural framing and the studs turned into wood. And then we went back to the base case and we used aluminum frame windows instead of wood. The base case for the building had wood windows. And we'll see what that means. This is my little slide about frost-protected shallow foundations. If you design it properly, it'll be something around a 74% reduction of the volume, 65% reduction of the concrete. Put in fly ash and slag, you can get a 74% reduction. So it'll be 1/4 the carbon footprint of a normal footing. And then windows. I didn't realize as I was doing this that the windows would be such an important piece of the carbon emissions. Not the energy performance of the windows, but the actual carbon footprint of the windows themselves. Aluminum is twice the carbon footprint of vinyl, and vinyl is twice the footprint of wood. See, these are nice, easy, round numbers to get your heads around. But I found a nice source which did a whole window analysis, including the glass in the frames. It's a pretty significant number. And so these are the variations. With the base case on the left, frost-protected shallow foundations reduce the carbon, the concrete, the green section significantly, and then a little bit more with the cement reduction. And then the rock wool took the bright blue section of insulation down by more than half because XPS has a pretty big carbon footprint. And then I took all of the steel out of the building and replaced it with wood, and I got the total down to about 20 pounds per square foot of carbon emissions. And then I went back to the main building and added aluminum windows, because really aluminum windows are a pretty common type of window for commercial applications, and that brought the base case up to 40. So that's a factor of 2, from 20 to 40 PSF, pounds per square foot of carbon emissions. For the different buildings. And not a whole lot of change in the construction cost. You could argue that frost-protected shallow foundations are actually cheaper. Insulated concrete forms, I just want to touch on them quickly because we said that we would in the description of the presentation. So pretty cool things without getting into detail about what they are and how to design with them. We've designed a couple of projects with ICFs, and we'll be designing more. The carbon footprint is pretty good for concrete. What I like about ICFs is you can add a lot of supplementary cementitious material and reduce your cement in your ICF forms. But you still need slab and foundation. This was from a previous study where I just looked at the wall, the foundation, and a section of slab on grade near the exterior wall. Structurally insulated panels, another really cool structural system. What I found is that it depends a lot on the type of insulation that you use. Polyiso, very efficient, gives a pretty low carbon footprint of about, I forget what the unit is. It's going to be a comparative thing, about total carbon footprint of about 2,000 for it was a 10 foot by 10 foot square wall assembly. If it's EPS, it's not too much different than that, because the carbon footprints of the insulations are similar. If you were to use XPS, it would be a pretty significant carbon footprint, about 9,000 by my calculations. Again, assuming all the blowing agents of the XPS go into the atmosphere, high global warming potential. So XPS really should be something that we should use minimally until they change the formulation, or until you know that you got a different blowing agent. Straw bale, again, not to get into the design aspects, although I think that they're very fascinating. There is stucco that is used as a parging on the outside and on the inside to make the straw bale work. And the reality is they're wide walls, so you need a foundation that's wide enough, and it's usually concrete, so your concrete footprint is actually relatively high. So it's a significant footprint. Again, we're not talking about energy usage in the final building. We're just talking about the carbon footprint of the building itself. So practical takeaways, and then we'll move on to Mark's presentation. Watch your windows, the carbon footprint of the windows themselves. Avoid XPS and closed cell spray foam. Dematerialize, but be careful about it. It's a way to reduce your carbon emissions, but you do need to be careful. We should consider the use of wood. It seems that wood has a significantly lower carbon footprint than concrete or steel, including wood frame windows. Pre-manufactured components generally have lower carbon footprints because of the reduced amount of worker travel. And in general, labor-intensive job site activities should be minimized. For concrete, we got some simple ideas that we had covered previously. So there's a lot of things that we can do if we are to be aware of carbon emissions of our structural systems. And so that's my presentation. I exceeded my 20 minutes by a few with the introductory comments, so I'll leave it to Mark to take it from here. Thank you.
All right, thank you very much, Jim. Great introduction to our panel here. I'm going to talk about a particular strategy, which is design for deconstruction, and it's a topic which has been I've been thinking about for quite a while, and we finally got some funding to actually do some research on a particular system, which I'm going to tell you a little bit about during my presentation. So what is DFD, design for deconstruction? Well, what is deconstruction? Basically, it's the careful demolition method of a structure where you try to preserve the materials as much as possible so that they can be actually reused in a future construction project. So we're not talking about recycling or going to landfill. We're talking about actual reuse of those components. And why would we do it? Well, there's some pretty obvious reasons. Increase salvage rates and recycling potentially. Increase the building end-of-life value. If you know that there's sort of a whole bank of materials in the building which potentially have value at the end of life, and it would be great if we could facilitate the ability to tap into that. Reducing the consumption of raw materials. And thereby reducing energy consumption, and of course on the other side, reducing waste and landfill demand. So what is DFD not? Well, it's a great strategy, as I'll hopefully show, for reducing the carbon footprint of buildings, but it's not a great climate change strategy, primarily because the benefit comes at the end of life of the structure, not at the beginning. And we know that climate change is an issue that we need to deal with sooner rather than later. But if we're looking long term, and I think we want to have low carbon construction far into the future, this is a great strategy to help that happen. And this is all about closing the materials loop. I mean, what is sustainability about? It's not extraction, use, and throwing away. It's about closing that materials loop, using those materials over and over again. So I just want to run through basically 7 fundamental strategies for designing for deconstruction. One is that we should design buildings that we want to be deconstructible, to have simple, regular layouts. When this building reaches the end of its life, hopefully 75, 100 years from now, somebody's going to go in there who has no familiarity with the building. you want that building to be easy to understand so that those potential components can be identified and there can be some planning in terms of what's there and what's of value. Here's an example of a building which does not have a simple regular layout, a building like this Frank Gehry building. It's a beautiful, well, I guess depending on your aesthetic values, building. But every component in this building is sort of custom made for this building. So, yes, maybe you can deconstruct it and reconstruct it in, the same building somewhere else, but it's not a good model for sort of mainstreaming DFD, which is fine. We're always going to have a few of these sort of buildings out there, and we need them. So this is talking more about our common building stock, the buildings that we build day in and day out. Layered building systems. This is a figure from Stuart Brand, an idea he actually got from somebody else about separating building systems. And if you're deconstructing systems, it's easy if they are separated. That simplifies the idea of deconstruction. And also adaptability comes in here as well. Mechanical systems often get changed out over the life of a building. Envelope systems often get changed out. By keeping these things separate, it makes it easier to do those sorts of changes. Now this building here is great maybe from a material efficiency standpoint because they've combined certain functions into a single component, in this case the precast concrete slabs, which serve to deliver mechanically conditioned air, as well as are a finish in the ceiling. So you're combining a lot of functions into one element, which is good on the one hand for an efficiency standpoint, but I think maybe is problematic in general from a deconstruction or adaptability standpoint. Second rule of thumb is actually this is part of the same one. Layered building systems. Here's an example of how you can separate those systems. And you can see a conventional wood frame construction on the left versus the system that was developed by Benson Wood, where they've actually provided an interstitial layer between under the floor where you can run services and keep those independent of the structure. Yes, more material, so there is an upfront cost, but the hope is that over time that'll pay back with the adaptability and future reuse of this material. Certainly if you're cutting on the image on the left where you're putting plumbing through wood joists and so on, it's going to make it harder to reuse those materials. Okay, the third one is simple standardized components and connections. This kind of relates back to the earlier point I made about keeping things transparent so that the deconstruction contractor can come in there and take things apart easily. And there are some interesting systems out there that have been developed that actually, almost making a kit of parts like an erection set, where you might have like this quick-on system, which I don't think caught on, but it was a great idea where you can kind of snap these different parts together, and it seems to me you could take them apart again and reuse them. Or this other system on the right, which is a system being used actually a lot in seismic territory, which again has the potential to be taken apart and reused. Rule number 4, or guideline number 4, removable fasteners. So let's avoid adhesives and welds because those are obviously going to make things harder to take apart. This is a picture from the APA, Engineered Wood Association, how you build residential wood construction. You got your I-joists, you got glue, you've got your plywood, everything's glued together. If you've worked with wood glues, these things aren't going to come apart very easily. So, maybe there's some ways to, using mechanical fasteners, that you can make that easier. Or, for instance, here, there's a system, Lindapter is a company that makes clamped connections, steel-to-steel connections, which, again, are reversible and would allow reuse of those materials. Using fewer larger members versus many smaller members also is a strategy. For instance, the timber frame construction on the left, those pieces are more robust, they're going to be easier to handle, fewer pieces to deal with, versus conventional stick frame construction. It's going to be more difficult, costly, and potential for damage of those components if you want to reuse them in the future. Salvage materials. If you want your materials to be salvageable, well, if you're using salvage materials, you already know that you've got something there that can be reused, because that's what you're doing to start off with. And this is one strategy where actually you're going to have a big early benefit too in terms of your carbon footprint, because really the only carbon footprint associated with using a salvage material, transportation, maybe some refabrication, that sort of thing. But it's going to be much less than for most materials than what you would have if you use virgin materials. Wood, maybe not so much, but certainly steel, that would be the case. And I would say, as my 7th rule of thumb, is to avoid most composite systems, composite steel concrete floor systems. They're really, you're not going to be reusing those components because of the way they're attached together. Maybe some composite systems like these SIP panels, if we can figure out how to connect them together in such a way that they can be taken apart, maybe the panels themselves, maybe you can't separate the OSB and the insulation, but maybe you don't have to. Maybe you can reuse that panel as a panel. So that sets the stage to our research project, which we're doing with Northeastern University. And we have actually a National Science Foundation grant and some other supporters for the project, which is fantastic, because this is something that's been bugging me for a while, and to finally have some funding to come up and to test a system that we developed, me and some of my colleagues, a few years ago, is terrific. So this is our conventional composite slab. If any of you are into commercial buildings, this is typically how they're built. You have your steel framing, you have your metal deck, shear studs, cast-in-place concrete, maybe a wire mesh in the concrete. These components are really not reusable. You're not going to reuse that concrete, the metal deck. Maybe you can extract the steel, but it's all pretty well tied together if you have shear studs there. And that's what you need for the composite action. That's the benefit of the composite system, is the concrete and the steel are working together, and so you can use smaller steel beams because they're working together. So it's a great efficiency strategy for construction. So we thought, let's think of a way we can, if there's a way to do this in a deconstructible fashion. So this is the system that we came up with, and basically it's a precast plank. It has continuous embedded channels in the bottom, and they're continuous, so you can move that supporting beam anywhere along the length of the plank. And the connection to provide composite action between the precast and the steel is done with these clamps, and such as these Lindapter type clamps that I mentioned earlier. So it can all be taken apart. It can probably all be reused. Maybe the bolts, we're not sure about those because they need to be tightened up pretty tight. But the rest of it, the idea is that all these components can be reused again in another building at a later time. This is what the floor plan might look like. We're thinking of sort of like wood decking, where maybe you stagger the end joints and allow some transfer of force from plank to plank. These planks are maybe 2 feet wide, so and they have it like a tongue groove type joint, just like wood decking, to transfer load side to side. It's we think the 2-foot width makes it a little bit easier to handle, and being able to stagger and offset the end joints makes the opportunity for more flexible reuse as well. So you don't have to have the end of the panel line up directly over a beam. So we've developed an archetype building, office building, to study what are the environmental impacts of using this type of system. It's a 9-story office building, steel framed, etc. And we performed a life cycle assessment of this building using a conventional composite slab versus using this deconstructible composite slab idea. Using SEMA Pro, we modeled material transportation impacts from the gate to the building site, because that's not normally built into the material models within the software. And we also accounted for by estimating the worker transportation to the project site, construction site, to take that into account as well. And we assumed for our base case that the DFD components could be reused 3 times on average. So the way we took into account the benefits of reuse is that we assume that the transportation impacts are the same for whether you have new materials or whether you have reused materials. Essentially, if you're reusing material, it needs to come out of the old building, maybe it gets transported somewhere to a storage facility, temporary place, and maybe it gets transported back. But the idea is, maybe that's roughly a wash, in terms of transportation of the materials. So if there is no reuse, and the top bar is our DFD building, and the bottom bar is our conventional building, our DFD building has slightly higher global warming impacts. One of the reasons for that is that the slab's a little bit thicker. It doesn't have the flutes in it, so we got a little more concrete and so on. So, our upfront costs in terms of environmental impacts are a little bit higher. But if you assume that those components get reused 3 times, look at this difference. You're cutting your global warming impact down by, say, roughly 70–75%. So that's huge. I mean, what other strategy can you use to cut your building footprint that much? And there's not many out there, really. Of course, this presupposes that it actually will get reused. You can do this great design for deconstruction. It doesn't guarantee that that's going to happen. But let's assume that, over time, as, we change building construction practices, that becomes the norm. This, I think, is feasible, that this type of deconstruction could become standard practice. So just a couple of conclusions. DFD offers tremendous environmental benefits if the systems are actually reused. Assuming, in the example I showed you, if we assume 3 times reuse, that cuts those initial emissions down by 71%. If we use it only twice, we still get cut by 63%. And if we reuse 4 times, so just kind of trying to bound the assumptions a little bit on what that reuse how many times it'll get reused. So, even if I'd say even if it's reused once, you're going to see some benefits to using the system. And just in general, this DFD concept, it's not something that we were ingrained to think about as we were, those of us who are designers. We're not thinking about end of life too much, and I think that's changing, which is a good thing. But this idea of designing so that we can take something apart changes completely how you think about design. You're not thinking about cast-in-place concrete so much anymore. You're trying to figure out ways to get away from that and use systems that can be reused. So it really changes your outlook. As I said, I think it's going to be most successful for kind of our routine buildings, low to mid-rise commercial construction and housing, those types of buildings which account for the majority of our construction. And these are the types of buildings that are likely to have regular repeating floor plans, simple construction, and relatively short lifespans. And the plus side is, I think this is starting to attract the attention of the design community. We've seen some excellent publications coming out on this topic, which I can give you references to those if anyone's interested. And that about finishes my presentation. So I think I've made up for extra time, Jim. So thank you very much.
My name's Russ Miller-Johnson, and excuse me, I'm a structural engineer up in Burlington, Vermont. But once you get up there, it's all kind of the same to a lot of people. It's just Vermont, so we'll let that be. So by now, probably on all your buildings, all the thermal break connections are being designed. All the structural thermal bridges are being reduced. Your mechanical engineer has accounted for that and has reduced the systems. And the energy modeler is very excited because they don't have condensation spots or hot spots or cold spots anymore. So this will probably all be just rote and very stuff you're already familiar with, right? So how many have been on a building like that where the systems were sized down because thermal bridging was reduced? That's great. That is great. Because 2-3 years ago, I said kind of the same thing, and only one hand went up. So that's good. Thank you. So I'm going to talk about just structural thermal breaks, breaks in, the superstructure, and really stay away from facade connections in just this short presentation. And the strategies are to reduce the conductivity of the penetration of the envelope. It's pretty simple. It improves the energy performance of the building, and it one thing that I've seen is there's a lot of visceral understanding of reducing condensation, like in lobbies and in doorways, and so there's a lot of acceptance for a little higher first cost, but a bit of thermal break being performed in entry areas to get rid of condensation and ice this time of year. Why do anything about thermal bridging? Because it appears that really buildings aren't performing according to the cookbook or the assumed assembly ratings of the walls and envelope. So in an attempt to get buildings to perform more as they are said to have been designed, we can attack that by getting rid of the cold spots or hot spots in the wall or in the roof. In these slides, I've tried to just have references or pull things from guides out there that we're using more. Obviously, the ASHRAE 1365 has been big, and the lower slide is from a British publication, and they're ahead of us, as I think everyone else knows. You'll know that some of that thermal bridging reduction is codified in Britain for certain types of structures. It is now part of a code up in the state of Washington, I think just in Seattle or in the state of Washington, to reduce the amount of conductance through the envelope. So again, why do anything? This is phase 1 and phase 2 of a hotel, and I worked on both of them. Phase 1 over on your right is a continuous ledge. There was debates when this building was going up whether it even met the Vermont Energy Code, but it went up. And on the right, it's just a spaced connection, and there's a FRP plate and some bolts in there to cut down on the conductance through. And so you can see just the difference in a very amateurish IR photograph there of the difference. On the right is the continuous ledge, and on the left is the broken ledge. So what are the strategies? This is from a insert that was in Modern Steel Construction that was done by part of the committee that Jim and Mark are on as well, and it's to utilize geometric separation. That would be you don't even penetrate it, you have outside columns. To use discrete bridging elements, cut down on the number of penetrations, cut down on their size, cut down on the occurrence. Use less conductive materials, stainless, insulated connections, FRP. And then the fourth is to use prefabricated or manufactured structural thermal break assemblies. Same chart from Building Green. 1 pound of CO2, this helps me think about it, is the size of that exercise ball. So rather than talking about energy here, I'm focusing on just what the carbon effects are. And when I say carbon, I'm going to just kind of glom all that together as to whether it's embodied energy or carbon footprint. So this is a building up at Dartmouth, and it's a pretty common problem for where the building comes up above the ground. This building has a basement, and the below-bearing wall comes down. There's a lot of residential construction. This is a multi-person residence. And the university was aware that they did have a lot of buildings where they had cold edges. So we proposed coming in with autoclaved aerated concrete and breaking the concrete and wood connection there, and also to give them a somewhat durable surface up above the ground. It's got a heavy coated stucco to keep the moisture out and to give it some durability. So what were the differences between using just masonry there or AAC? So ran a therm model with a colleague, and that is not the current slide.
They both look about the same, really.
Yeah. No, this slide has a carbon comparison on it. Well, I'll have to, yeah.
Well, what were the, yeah, 2 versus 5?
So that's an AAC wall, reinforced at 48 inches on center versus a masonry wall, concrete masonry unit wall. So those are the effective conductances there. So what I did was I looked at the difference in the carbon for that building, one band all the way around the building, and the carbon embodied in the construction, and I looked at the carbon embodied in the AAC. And the AAC comes all the way from Mexico at this point, near as I can tell. Somewhere Texas, Mexico, they're not very clear about where it originates from, but it's somewhere there. And I added in that travel time. I also added in about that there's about a 7% absorption in the concrete masonry over the life of the masonry. So I gave 7% back to the masonry. And in essence, the carbon payback was just a couple years, if I can put it in those terms, that the carbon initially for the CMU was less. It's more locally made, even though it's a Portland cement product. The AAC is only about 20% less in the manufacturing as far as carbon. But because of the insulative differences there, the difference turned out to be a payback in carbon of just 2 or 3 years. So the takeaway is that AAC, even though it's hard to get locally, it's not hard to get from what I've seen. We're using it in a lot of jobs in small and larger quantities, door sills, all the way up to floor panels. We just did a job with floor panels as insulated floor. What are the other alternatives? Well, there's proprietary block out there that's insulated. This is Omni block on the left. May or may not be used up at Spruce Peak on a small project. And this is the an agricultural-based cement fiber block on the right. So then another strategy to mitigate thermal breaks is stainless steel in lieu of carbon steel. Stainless is about 1/3 less conductive, pretty straightforward calculation there. These were, I'll stop here, just go back. These are exposed columns on an entry structure up in Waterbury, Vermont, a manufacturing facility. And the stair is internal, so we had to connect the stair to the columns through the envelope. So we used stainless steel there. It was a food service manufacturer, so they're pretty aware of condensation, and that made the difference in getting it on the job. So I ran, here rather than therm, I ran a spreadsheet difference, just simple conductance in terms of summing up the different conductances and their areas and seeing what the effects were and the differences are. And I really apologize. There is a slide or two here on carbon difference, which, if you stay later, I'll put them up. So what I learned was the good news is that stainless apparently uses a lot less energy when you recycle it. So that's end of life, which I didn't know, but seems to be pretty clear in the literature. But stainless is also 4+ times more carbon intensive than carbon steel. So the differences in carbon are pretty big as far as getting it in. And when you look at discrete thermal breaks, you can look at it one or two ways. What's the effective energy difference right at the connection, or as a function of that entire wall? So here I looked at it as a function of the entire wall minus the glass, just the insulated panels that it went through. And the payback period was about 5 or 6 years. That is, stainless started with a bigger hole than the carbon steel did, but the payback surprisingly wasn't that long. Now, if you look at it just in terms of the area affected by that connection, which, you know, it's only a 1 1/4 inch plate. I think it's about 1.5 foot high. The payback would be very long to equal the carbon that you've used to offset. And I used some very basic energy modeling assumptions, which are the same as in the modern steel construction insert. I tried to keep a consistent basis. So modern steel construction has a thermal bridging insert from March 2012, where those assumptions are, and I think it was 11 cents a kilowatt hour in that model building, just to give you some idea of what the basis were for these comparisons. So what are the alternatives? Here are some insulated thermal break connections. These are up on a manufacturing facility in Lebanon. And this is on a building, it was on a museum where they had to have high-end moisture control up in Vermont. And these are, these connections went through several mitigations, variations. And here the mechanical engineer did want to pay attention, and because the space is humidity controlled, it didn't sound very well, but they were on board, a team approach, and we ended up at this point for just the humidity controlled overhangs, the overhangs in the humidity controlled areas. And those are FRP plates and stainless bolts. And the first time they went in, they didn't use stainless bolts, but it's pretty easy to see. So you can see the upper right one, no stainless, pulled them out. Lower left, put them back in, stainless. And here's not a manufacturer or a specified system. This was a canopy connection using conventional or pieces of insulation, bolts that are countersunk. One thing about these connections is, depending on the load, you've got to look at whether you're actually putting back more steel than you would have had you just passed the element through, more steel in the bolts versus what the element is. And here we couldn't get the rod through. The rod actually would have been less steel, but they didn't want to let it pass through. So it's a pretty hefty bolt area, but it is broken and insulated. And here's a project, another alternative to steel is don't use steel. This is a SIP overhanging the edge of a building. So we don't actually have any steel protruding the envelope because the insulated assembly is the SIP, and it hangs on out over the edge. Incidentally, this building has a wood curtain wall system. It's engineered lumber as wood girts holding up the metal panels as well. So another strategy is to use insulated thermal break connections that you specify or come pre-assembled in a way. And here's a problem where the structure comes down and it's open air underneath both these buildings, and one is insulated and one is uninsulated. The technology is pretty simple. A lot of you have probably already done it. It's in freezer warehouses. It's just freezer column block insulation set down there, specified. Here are the differences in just based on thermal imaging. And so I used those to prepare a slide that isn't going to be here. There, I only looked at that footprint, that square that is the column top, as the area to study for the carbon equivalency of insulating versus not. And so there, the payback, in essence, of the initial carbon for the insulated, because the foam is high and these pads, near as I can tell, are made somewhere out west, generally in the Oregon, California area. Even though we specify them, because of the supply chain on a lot of these items, it's really hard for the construction manager to find out exactly where they come from, believe it or not. So the payback was in the 30 years, if you just look at that small area. Now, obviously, that floor area has a larger effect, or a larger tributary area, but if I just looked at the 1.5 foot square of that connection, the payback was 30 years, which in the world of construction today, there's a lot of first cost pressure on a lot of jobs. Seems like an eternity, but you know, Mark showed a building from 1998, which to me seemed like a long time ago, the Geary building. So trying, in some ways, 30 years isn't really so long. And the calculations I ran are approximate, but even if you're off by 5 years, there's no way to really predict the future cost of energy or the way energy might be made in 30 years. Hopefully it'll be less carbon intensive. That may extend that payback period on the carbon, but it shows that, to me, that insulating connections is still a pretty good approach. Now, there are other ways to do this. One's the old-fashioned way. You just insulate back up in the building after you stick your element back out and you insulate back in the building. Or you insulate around your overhanging edge. Another alternative is to try and, sorry, turn my head, is to try and use a manufactured thermal break connection, which we talked about before, but in a somewhat unconventional way. I attached a slide because those thermal break connections are probably still at the steel fabricators. We ended up they built them conventionally, and we had to change to stainless plates at the last second. They forgot to. I think we're in here twice. There we go.
Maybe your slides are here.
Hey, what do you know? Okay, so let's see if I told the truth from memory. The AAC was a little higher, and this is for the whole building. This is for 180 square feet all the way around. And I tried to take a transportation penalty, but I know that they did not come up FedEx ground all by themselves. I know they were put on a truck. They were identified as a long lead item, and they came, in a full truck load. So, so if the difference was about 400 pounds in the initial construction, and it's 330 pounds per year of savings, then it's about a 2-year payback. All right, and on the stainless, you can see the big difference in the initial, and that's primarily because of the manufacturing or the manufacturing load of the stainless, not so much the fabrication. And then if there's, and again, this is on the, if I average those connections out over the area of the facade panels, the insulated panels, then it's about 6,000 pounds per year. So say a three year to get back even. And the uninsulated I just called the base design, and I just figured out what's the load of the insulated. And all I used here was the difference in temperature from those thermal imaging photos, because I took them within 10 minutes of each other. Those two buildings are real close. And so I did not do a therm analysis. I did not do a spreadsheet analysis. I just did a photographic analysis, yes.
What is that insulated material and what's its compressive strength?
Oh, between 1,000 and 2,500 PSI.
And it's, what's the material?
It's a high-density foam. 25 years ago, you might have used a tar-covered oak block on a freezer warehouse to keep the ground from freezing, and then these came out somewhere along that line. And it's the same, it's been the same product, in my experience, for the last 25 years. But now we're finally using them out of the ground and just to provide insulation. And here, if I just look at that little area, it's only 50 pounds of CO2 a year. Now we say 50 pounds. I certainly spent way more than that driving down here from Vermont in a diesel. So, and that's a picture of it right there. Not in that application, but in a different application. So those come pre-drilled, and you got to make sure the anchor bolts are longer than standard. Usually fabricators miss that, so.
Okay, that's Russ.
Now we're just going to take a couple of minutes while we get the right slide for Kara. Slide presentation. Apologies for the technical difficulties. My bad. Does anybody have any questions or for now? In front?
That's a question for Mark Webster. Yeah. You also mentioned, all of you folks have mentioned carbon. And I'm going to sort of ask you the same question I asked Jim. When you talk about carbon emissions, these materials aren't sitting there emitting carbon. The carbon emissions are embodied fuel. Do you know if it's primary energy or secondary? What energy is embedded in those calculations?
I believe that the software like SEMA Pro uses the primary energy emissions used to generate the electricity or other fuels to produce the products. And if anyone thinks it's different, who's an LCA specialist, speak up.
It's really important because electric arc furnaces, electricity, has a very different PE factor than natural gas. So we need to at least say what we're measuring.
Yes, you're right. And
because Russ's, what he's presenting, he has to also say, since he's comparing embodied energy with operational energy, what the assumptions are, or these numbers can be off by some significant factors.
Yes.
I just wanted to add that it's not only energy, though. Portland cement emits carbon emissions that has nothing really directly to do with energy, and so do blowing agents and insulation. So it's not a one-to-one. It is more complicated, unfortunately. Time for maybe one more question? Yes?
You did that calculation of that hypothetical building, and you ended up with so many thousand pounds of carbon. What was that number? Was that like 30,000, or was it?
I remember about 35 pounds of carbon dioxide per square foot of occupied building.
Or I might be thinking of what I was curious about was the relationship of the building materials versus like the transportation. Like you had that crew, that building crew was 14,000 pounds of carbon just to get them there and back. And so I don't know, I was trying to put into perspective the carbon output of the materials versus carbon output of like day-to-day life. I mean, I don't want to minimize that.
There's a
I think it's important.
fascinating topic that we don't have time to cover.
Very good.
Very important. I give you Kara.
Hi everyone, so I realize I'm the thing standing between you and coffee. So with that in mind, I'll try to get through these really quickly. First off, who am I? My name is Kara Peterman. The program says I'm from Johns Hopkins. I actually received my PhD from there about a year ago, but now I'm a postdoc at Northeastern University. So I'm local right here in Boston. And I thought I would share with you today sort of an ongoing research project that I'm working on that's related to thermal bridging in cladding systems, specifically in steel frame buildings. So I'm not offering any sort of alternative to steel frame buildings today. Instead, I'm encouraging you to love them and design for them. Anyhow, a bit on our project team. You might recognize some familiar names from here. Jim and Mark, as you've heard from earlier, are both active on our project. Representing the eggheads of the world is myself and Professor Heger at Northeastern University. And then furthermore, we also have a lot of input from Simpson, Gumpertz, and Heger beyond Mark. We have quite a number of interested funding partners, not including, but not limited to, the National Science Foundation, the American Iron, the American Institute of Steel Construction, the American Composites Manufacturers Association, the Charles Pankow Foundation, and many other alphabet soup acronyms as well. So Russ actually provided a fantastic introduction to what a thermal bridge and a thermal break is, but I'm going to go through it again anyway because I have my own way of talking about it. Then I'll take you through some of the archetypal thermal bridges and steel structures that we're identifying. Then our mitigation strategies as a part of this research project, some thermal performance, a bit on our experimental test program, and then a bit on our future work and conclusions. So, as Russ talked about, thermal bridges are structural elements that span the building envelope and result in heat transfer between building interior and exterior. So the great thing about being in Boston and talking about this now is it's cold outside, it's warm inside. We want those two things to be ships passing in the night, when in reality, they're not. And as I've shown in my little plot at the bottom, this is especially true. Thermal bridges are a real problem when you have steel structural elements, more so than stainless structures, concrete structures, and of course timber. Professor Heger and I at Northeastern, we were both steel researchers. So as I said, we're sticking with steel here and working with ways we can mitigate thermal bridges and steel structures only. Some pretty pictures for you. I just wanted to show a picture of, I guess you can call these more effective thermal break strategies in the Aqua Tower in Chicago and the Burj Khalifa, and you can basically see that the outside is, it's the temperature of the outside air, which is what you want, and the inside is the temperature of the inside air. You want those two things to be totally separate and not have this meshed together energy problem. So what about a thermal break? So it's exactly what it sounds like. The idea here is that thermal bridges must be physically broken to prevent an energy loss, and thus we have the term thermal break. In our case, we're talking about splicing the steel member in some sort of way and inserting a thermally improved material or system in that break. And of course, I'm a structural engineer. These breaks have to be just as effective at load transfer. So it wouldn't be a very good strategy if we said, well, hey, it was great at energy transfer, not so great at holding the building up, because then we would be terrible engineers. So what specifically am I talking about? Which cladding details are we most concerned about? So first off, we chose an archetype building with the help from our friends at SGH. Some basic information. We sort of chose two potential locations, one in LA and one in Boston, so you can imagine the differences in insulation, for example. Pretty basic structural configuration, 3 bays, 13-foot story height. It's an SCBF. And again, most importantly, this is a structural steel building with concrete plank floors. This is a brutal box building, not really much to see here. And thermal bridges that we're most interested in here, I'm going to begin with two types of shelf angle, and this is for supporting a brick veneer. The first is our slab-supported shelf angle, and the second is kicker-supported. And these two drawings right here, if you're familiar with the ASCE Design Guide 22, which is for cladding systems, these drawings will look familiar, but they look really messy if you're not. Essentially, I'm going to step away from the microphone. Hope everybody can still hear me. What we're most concerned with here is there's one shelf angle holding a brick. In the kicker, the shelf angle is actually hung from the slab by a metal element. And you might think, well, it's just holding a brick load. What do we, why do we care so much? You don't want your bricks to crack. And so what we find is that these shelf angles are actually deflection limited, and they end up being much stiffer than you would expect for the loads that we're examining. Two more archetypal thermal details that we're looking at. The first is a roof post detail shown on the left-hand side of the screen, and on the right is a canopy beam. So imagine something for an overhang in a commercial building. So Russ went through some mitigation strategies. We're actually looking at basically three of these. The first involves using a thermally improved shim, and we're talking FRP steel foam, which is an interesting concept if you haven't heard of it, and of course stainless steel. Adding a shim actually takes advantage of this concept of intermittent spacing. You no longer have your shelf angle bearing against the entire continuous concrete slab, for example. With a shim, it only bears at connection points, which is a huge advantage. For one thing, the shims are also easy to install. Most of these cladding details are installed and adjusted in the field, so we don't want anything too complex because that's really going to mess with a standard construction flow. And then finally, these shims are actually structurally promising, so we're interested in them, and we believe they're worthy of significant research time. Of course, there's the solution to replace the entire structural steel member with thermally improved member. So if you're familiar with common pultruded FRP sections, they make sections that are much similar to the steel sections, so you can have an I-beam or an angle or these types of things. But available member sizes are actually they don't go that large. So even for our brutal box, building, we find that we're maxing out the pultruded sections that are available. And making a custom section that's bigger and thicker is pretty expensive, and it would only really be worth your time if you were doing a lot of buildings or a very large building. And then also, these FRP members may not actually be structurally effective for our loading applications. So while we are still interested, we think actually most of the promise lies in some sort of shim. And we are now beginning to research manufactured thermal break assemblies as well as a comparison. A lot of challenges here. Structural integrity being foremost among them. Essentially, I have a lot of structural engineering jargon here. We're very interested in their performance, of course, under monotonic loads, which is just your standard static load. Cyclic loads, which would include a seismic effect or a fatigue effect. Creep performance. Creep is essentially prolonged load. So you want to know that your connection or your thermal break is going to stay the same over 50 years. Obviously, we can't do a 50-year test in the lab. We can make some assumptions and extrapolate into the future, but those things are important to us. Connection performance. You can't bolt steel and FRP or steel and steel foam together and expect it to behave the same as steel and steel. So that's something that's a research focus for us. And then finally, performance under elevated temperatures. The reality is we expect buildings these days to behave well under a fire, not just hot summers in the Middle East, but under these more extreme loads. Also, as I mentioned, field adjustability is important. We have to be able to install these things in the field and adjust according to construction. So if you expect 13-foot stories, one of your stories comes in at 13.001 feet, we have to be able to adjust for that on site. There's also the geometric constraints. We have a limited wall cavity to work with, and of course our strategies have to be thermally effective. Furthermore, FRP to steel connections, which we are very much hoping will work out, have not been validated in the experimental literature. There's a lot on FRP to FRP connections or steel to steel, but FRP to steel is relatively unexplored. Furthermore, FRP to FRP and FRP to steel connections are not clearly approved for structural use in National Building Code specifications. So even if you as an engineer, you as a designer wanted to use one of these, it would be very difficult to actually find guidance in the North American specifications. So I'm just gonna, we really don't have a lot of time to go through all of our proposed thermal breaks, so I thought I would highlight just a few and give you an idea of our research direction from there. This is the same shelf angle detail, and it's just drawn differently. And you can see the shelf angle is in red at top, and essentially when we put a shim in, we aim to put our shim right between the concrete slab and the shelf angle. And our idea for field adjustability is, you can see at the bottom, we usually depend on some sort of stud and long slotted holes in the shelf angle, but we actually now propose this adjustment plate, we call it, which is which in our detail would be a stainless plate, which is welded, and then you can essentially fit your shelf angle onto the plate. So with this adjustment plate, we can look at a variety of different shims. And now an FRP shim is pretty easy to visualize. You take a plate of FRP, you drill a hole in it, and you plop it on. No big deal. We're also looking at using stainless or FRP tubes or rectangular sections as a type of shim. Because as you can see, it achieves our intermittent spacing. You achieve additional insulation from an air layer up top. And we believe it could be structurally effective as well. At the bottom is some basic ideas on how we go about using shims for a roof post or a canopy detail. So the shim idea is pretty straightforward. We also have some ideas using FRP tubes with a steel tube sleeve, and then of course stacked FRP shims to increase the thickness there. So I'm just going to move on quickly and go straight into touch on a little bit as to the thermal performance of these. And I just wanted to demonstrate to you in this brief presentation that our preliminary thermal models demonstrate an efficacy in our proposed solutions. And you can see at the bottom, these are heat 3 models looking at the slab supported shelf angle. And using an FRP shelf angle, we have a reduction in thermal conductivity of 49%, a shim 48%, and a stainless steel fin plate of 23%. But one thing we are questioning is how much improvement is good enough. Should we be seeking 100% reduction? Should we be seeking 20% reduction? So that's a research question for us. And of course, this tells us nothing of the structural behavior. This is our test matrix. It might be hard for you to read, but essentially we're interested in testing. When you say FRP, there's a million different FRP things you could be talking about. Resins are different. The reinforcing material is different. And so we have essentially our unmitigated details, vinyl esters, proprietary products that already exist, steel foam, etc. This is our test rig, which actually exists at Northeastern University. I'll show you on the next slides. Really, this is 2 separate test rigs here, but essentially what we're doing is loading our shelf angle so that we test the performance of the shelf angle here. Our shim is right there, and then we can sort of examine a real load situation. This is a different direction from the actual cladding detail, so if you remember the shelf angle and the cladding detail is like this, we sort of flip over on the side. For our beam and cantilever test, I know this is really illegible, but essentially we are concerned with cyclic performance here. We are testing all the different vinyl ester, polyester, phenolic resins, and are looking to do it in this type of rig, which will be coming soon at Northeastern University. And so this will essentially be a cantilever test with using dead weight as an axial load for roof posts. These are large actuators, 200 kip capacity, so 200,000 pounds, and 4-foot specimens. So this is all in the realm of large-scale structural testing. Connection testing. Did I skip a slide? No. Okay. So as I mentioned, we have this issue where FRP to steel connections are not readily approved for use, and part of our project is to approve them for use. And as such, we are again going through using this type of specimen to test how adding these FRP and steel foam and stainless steel shims affect steel-to-steel connection performance. So the idea is you essentially have steel and you have a fill that's something else. And we need to know if that fill reduces the connection capacity by 85%, by 15%, by 100%. So we can basically create equations that will allow for informed design. Creep. As I mentioned, prolonged loading is a huge deal when we're considering structural steel design, because structural steel, for the most part, does not creep. And FRP, if you look at the literature, there's very little available for the type of loading we're talking about. So when you have a shim, we're looking at compression in the plane of the plate. And so we're questioning, does the material experience strain at prolonged loads? And we're talking about 1,000 hours, 8,000 hours, and 1 million hours. And so we're actually currently developing a test standard, since weirdly we're the first people to examine this particular issue. And of course we'll be examining a range of loads. So 90% maximum capacity prolonged load, 40% maximum capacity, and a lot of things in between. So as I mentioned, this is an active research project now. So in terms of current and future work, we have our experimental test program. I showed you a lot of setups for a lot of tests. That's all in my not so distant future. We have the structural analysis of the tested specimens, condensation analysis, and then the ultimate goal, of course, is to form recommendations for design. So with that, we've reached the end of the presentation, and I'd be happy to take any questions. Anybody? Yes.
FRP, I'm assuming, is fiberglass reinforced.
Yes, I should have led with that. Fiber reinforced polymers.
What's the conductivity?
The conductivity? Well, it will depend on your units here, but I believe it's 4 BTU per Fahrenheit squared per something. It's a what?
It's an R of 4 here.
Yes, R equals 4. Anyone else? Any questions? Oh, yes?
Do you have any preliminary indications on creep or failure on the fiberglass? Have you done any testing on it yet?
So the question was, do we have any indications of preliminary performance for creep of the FRP? We ourselves have no tests, but if you look at creep for other, like for tension, for compression in a different direction that folks across the world have done, it really depends on the resin and the fiber combination. So you'll see some of them experience relatively little creep, even at 8,000 hours, but some experience quite a bit. And this is one reason we have such a strong need for it, is because it's so dependent on the specific material that you're using. So we'll see. Stay tuned.
All the other presenters talked about the carbon
Yes.
emissions and everything. You didn't touch on that.
Nope.
Do you have any data on?
Nope, not at this time. This is a preliminary. This is primarily a structural investigation, but perhaps in the future we'll be looking at these costs. Yes.
Did you say steel foam?
Yes.
It's a product I'm not familiar with.
Yes, it's a very cool product. I should have brought my piece of steel foam with me, but it's an aerated steel. So you can imagine steel with carbonation bubbles in it. And you can form it by either adding bubbles or by making these tiny centered spheres. And essentially, it's like that phloem stuff maybe that was popular in the 90s, but these little balls of steel that are hollow on the inside. But it's thermally improved from carbon steel, standard steel, because of all of the air that you entrain. Has totally different structural properties, of course. So it's kind of a niche market that we're thinking could have applications in thermal brakes.
Where is it used?
So currently it's manufactured primarily in Germany, but if you were looking at applications in the US, one of the biggest applications is in race cars. A lot of them will have a steel foam bumper so that when they have a head-on collision. The steel foam actually absorbs much of the energy there. Anyone else? Yes?
If there's any particular carbon calculators you recommend you're working with?
I'm gonna punt this question to somebody else.
Mark can answer that question.
Well, the question was about whether there are carbon calculators that we like to use. And on the structural side, which is we're all structural engineers, so that's kind of what we know the most about. Our committee did publish actually a carbon white paper, which is available online, and that we went through and kind of summarized the best data we could find on the carbon emissions associated with various structural materials, and are actually working on updating that now. So at least for structural materials, I'd point you there as a good source of free, readily available data.
Which is where, Mark?
I would, it's on, if you go to the SEI sustainability.org website, SEIsustainability.org, there's a link to that white paper on that website.
Plus, you get a glimpse of everything else that the committee's been doing regarding sustainability. It's probably time to say thank you for being here.
If you have any other questions, just talk to us afterwards.
Please do.
Yeah.